Okay, so let's talk about the physiology of vision. Last time we had finished our conversation with the discussion of basic refraction of the image in an eye, right? Makes sense? So today we're going to talk about visual pigment and how visual pigment can convert light into a nerve signal. Okay? So we're going to start with the basic structure of the visual pigment. So the molecule, or a complex that we call visual pigment, consists of a protein component that is called opsin, and a rather small organic molecule. I'm going to draw like this, just for the sake of it, just called retinol. Okay? Does that make sense? Now, it's not just retinol, it has a name of 11-cis retinol. 11-cis basically describes the structure of one of the double bonds in that bond. Now you can see that 11-cis retinol and opsin together, they form visual pigment that is called rhodopsin. When you expose rhodopsin to light, okay, here's a couple of things that happen. First of all, 11-cis retinol gets converted into another form of it that is called all trans retinol. Okay, does that make sense so far? Second, it separates from opsin. So you see these two structures, opsin and all trans retinol, at this point are separated. Clear. Okay, good. So the obvious question that I was asking when I was learning this, and you should ask now, is why the hell is that important? Turns out that this separation of all trans retinol and opsin serves as the initial signal in the chain of events that result in the generation of graded potential and ultimately action potential that reaches your brain as the signal about you seeing something. Does that make sense? Now, how can you convert it back to the original form? Well, two conditions. If all cis retinol is converted to all trans and separates from opsin, it happens in the light. And in order to have it back, you need to do it in the dark. Does that make sense to you? I mean, if it's exposed light, that's not going to happen. In order to come back, you need it to be dark, and you also got to use A&P. Okay? The external source for 11-cis retinol, as you may have read already, is a vitamin A, because sometimes this molecule gets destroyed, something happens to it. So you need to constantly replenish. And the absence or low amounts of vitamin A riot due to the condition known as lutein or night blindness. You good so far? Keeping that in mind, we will draw a scheme of signaling that occurs in the rods and cones in the retina of your eye. Does that make, and we're going to kind of build one on another. First of all, these visual pigments are concentrated mostly in the outer fiber of the photoreceptor cells on the folds of the membrane. Does that make sense? They're called plates. So basically, if you have folded membrane, it means that there's way more surface area that allows you to accommodate more visual pigment. Does that make sense? Okay. So here's what happens during the scene. Wait a minute. So let's give some names here. Okay, so this is what happens in the dark. So you see some structures. First structure is visual pigment, right? This is the membrane. So that's membrane. And this side is the cytoplasm. Now, this is rhodopsin. On the cytoplasmic side of rhodopsin, there is G protein. This molecule here is the enzyme called PDE, which stands for phosphodiesterase. You will see its function in a second. Now, this is a voltage-gated, ligand-gated channel. Now, what is the ligand for that channel? I'm going to put the ligand right away. Cyclic GMP. Okay. So this is ligand-gated channel. You good so far? So you've got no dark, there's no light here. There's no light. Here's your rhodopsin, here's phosphodiesterase, here's the channel, and the channel is open because cyclic GMP is bound to it and it keeps it open. Does that make sense? So this is cation channel, which allows two ions to flow across the membrane. One ion is calcium, and another ion is sodium. Okay. Good? So, how are they charged? What is the charge of those two ions? Don't mix it. Much easier when you break it. Positive. When you have positive ions flowing into the cell, the cell becomes more positively charged. Do you remember what kind of polarization there is? D or higher. Positive ions, depolarization. They depolarize the membrane. They reduce the difference between inside and outside. So cell becomes depolarized. Does that make sense? Let's draw this up. Okay, so that is going to be the first cell here. Here. This is your photoreceptor cell. Okay? It is depolarized. Now, you remember, depolarization, is that a synonym for cell being excited or inhibited? When cell becomes more positive, is it excited or inhibited? More positive. Excited or inhibited? Excited, yes, excellent. And when cell is excited, it starts to release inhibitory neurotransmitter. Okay, it releases neurotransmitter. Let's start with this. So we've got neurotransmitter. Okay. And this neurotransmitter is inhibitory. Don't get me wrong. It is inhibitory, not because cell is depolarized. It is just inhibitory. That's the neurotransmitter that photoreceptor cell releases. Are we good? Now, this neurotransmitter acts on bipolar cell. Okay? So that's bipolar cell. This is photoreceptor cell. Okay. Now, inhibitory neurotransmitter. What it's going to do to bipolar cell? If it's inhibitory, it's going to inhibit. Excellent. And inhibition means that the cell is hyperpolarized. And when the cell is hyperpolarized / inhibited, it does not release any neurotransmitter at all, and there is no signal. Does that make sense to you? Now, look very closely. Depolarized photoreceptor cell releases inhibitory neurotransmitter, which inhibits and hyperpolarizes bipolar cell. And as a result, there is no transmission of a nerve signal between bipolar cell and a ganglion cell. There is no signal reaching the brain. This is why you perceive this as dark. Mind clear? Good? Now, let's take a look what happens, and I will start showing at the bottom to make it parallel. Equally, if you want to come closer, it's totally fine. So I'm going to redraw that same picture here. With some minor changes. Okay? Okay. So, like, okay, when rhodopsin is exposed to light, what happens to 11-cis resin? It becomes all trans, right? And gets dissociated from opsin. Am I making sense of that? So that's 11-cis. Now you see this G protein? See the G protein? When this happens, when 11-cis retinol is changed to all trans and dissociates from opsin, that activates G protein. So G protein activated G protein binds to phosphodiesterase. The binding of G protein to phosphodiesterase activates it, and activated phosphodiesterase breaks down cyclic GMP to GMP. Are you with me so far? Now look at this. What keeps this channel open? It's cyclic GMP. Am I clear? This is a key that keeps the channel open. Are you following? This key is destroyed. When key is destroyed, what happens to the channel? It closes. Does that make sense to you? Channel closes, and sodium and calcium cannot diffuse into the cell anymore. Good? And suddenly, the diffusion of positively charged ions stops. No more positively charged ions get into the cell. How does it change the membrane potential of the cell? Make it more. Yeah. Cell becomes hyperpolarized. It becomes more negative. So, out of a sudden, well, not out of a sudden, but your photoreceptor cell becomes hyperpolarized. Hyperpolarized cell is the same as the cell that's inhibited. Does that make sense? Which means it doesn't release an inhibitory neurotransmitter anymore. So your bipolar cell is not hyperpolarized anymore. It's not inhibited, so it is depolarized. And depolarization of bipolar cell leads to the release of excitatory neurotransmitter which acts on ganglion cell and, in ideal case, generates action potential. Does that make sense? Let me walk through this one more time. Here's what happens in the dark. In the dark, well, nothing happens in the dark. Okay, nothing happens in the dark. Here, the channel's open. The calcium and sodium diffuse into the cell, exciting. So your photoreceptor cell is excited and depolarized, releasing neurotransmitter, which is inhibited, which keeps bipolar cell inhibited. Okay, bipolar cell does not signal to ganglion. Okay. Now, in the light, light changes the conformation of 11 cis to all trans, and all trans dissociate from oxygen. That dissociation activates G protein, which then migrates to phosphodiesterase, activating phosphodiesterase. Phosphodiesterase starts the churning up cGMP into GMP, essentially taking out the key that kept channel open. Channel closes, calcium, sodium do not diffuse into the cell. The result of it, hyperpolarization of photoreceptor cell, no neurotransmitter is produced anymore, no inhibition of bipolar cell becomes depolarized, starts to release excitatory neurotransmitter. Make sense? I usually compare it to this. It's a dad, it's a girl, it's a boy. So dad watches over girl so she cannot talk to her boyfriend. Dad falls asleep, they can chat. Make sense? Couple more things. First, more of them I like, but just to remind you, on the level of transmission of visual information to the brain, what I want you to know. So from the retina, signal goes to thalamus, and that is really important because if you think about it, many parts of the brain require communication and require visual signal. For instance, it can be cerebellum, visual cortices, thalamus, regulate your sleep-wake cycles. Okay. Good. Now, last little bit about the eye. I just realized I do not agree here. It's a bit of a shame, but it's okay. We can do it schematic. So imagine that these are your eyes. Doesn't matter which one is which. Say that's left. That is right. Okay. This is your brain. Okay, so that's left hemisphere. And this is right hemisphere. Okay? You with me? Now, not much change. Once they use different colors, and then we'll see why. So, yeah. So fibers from the right eye, they go to the right hemisphere, they go to the left hemisphere. Am I making sense? Fibers from the left eye go to the left hemisphere to the right hemisphere. So far we're good? So this part right here, up to here. It's granular nerve. The part that is here, up to right. And this part in the center, up to. Yeah. The word chiasma in Greek means crossing. And you can see that the fibers are crisscrossed. Does that make sense? So I have two nerves that reach chiasma, and then some fibers from each nerve go to the ipsilateral hemisphere, some fibers go to the contralateral. Good? So let's think what happens if you get a damage to the optic nerve. Can you get the information from the left eye? If you damage the nerve, not the tract, the nerve, can you get the information? Look at this. No. That's it. That's it. All visual signals from your left eye stop dead in the tracks. Does that make sense? So you'll, even though your eye may be perfectly fine, there's a damage to a nerve, tumor, stroke, something like that. You're done. You can't see with that specific eye. Am I clear? So what if you have a damage in this optic tract? In this hemisphere, can you get the information from the right eye? What about the left eye? So you still get signals from both right and left eye. However, not all of them. What does that mean physiologically in terms of the experience? You get a damage to the nerve, in this case, the right eye. This is what's going to happen. Okay. You're going to see things with one eye. Make sense? And you're going to lose your depth perception. Because you have depth perception due to the overlap of visual fields from two eyes. Am I clear? Think about it. Visual fields in the periphery, they do not overlap. So for instance, right here, that visual field right here, it's entirely my right eye. The visual field right here is entirely my left. So you can't really be very positive about the positioning of things on the right side, right periphery, left periphery. But in the center, I'm pretty confident. Does that make sense? If I would have a ball and I would try to throw it to Catherine, I mean, I probably would be okay. She would be able to catch it, even over the plexiglass screen. Okay? Now, if hypothetically, well, I'm going to tell you if I'm closing my right eye, good luck with that. I'm really short-sighted in my life. But even with my right eye open, I would have a hard time properly targeting. We lose our depth perception. Now, if you close one of your eyes, well, you can close it now. Look at me. Can you tell that I am in front of the whiteboard? That I'm closer to you than the whiteboard? Honestly, yeah. And this laptop, is it closer to you than I am in relation? Right? It's closer to you, right? Now, you can say, that's it. But you can say, wait, how do I lose depth perception? It still tells things about not losing completely. Like, you know that if you can see whiteboard behind me, I must be in front of it. But try to play any game that includes, for instance, movement of a ball. I gather you play soccer. Try to play soccer being one-eyed. Your precision in terms of passing and shooting will suffer dramatically. Does that make sense? That will apply to kind of basketball, football, anything. Okay, this is what I mean by it is really hard to correctly estimate the distance. Now, there's a damage to your optic tract. You're not losing depth perception. You're losing field of view. Because some fibers that collect some of the information from the retina are going in. You see that? So yeah, you are losing some visual information, but not all of it. And you will still retain depth perception. Are we clear? Any questions on the vision? Anyone can I kill the soul, or you want to take a picture? Entirely up to you, totally fine with it. Okay. You go ahead, I'm just pausing there. So with that, we're going to talk about the last topic of special senses. Going to be hearing and then that. Hearing will take the most of our time. Balance will take 5 minutes. Okay? And here's what I'm going to do. You'll have your models. And I have model, which I'm going to try not to forget to demonstrate. Okay? Good. I am going to outline all the structures in the middle, and the outer, middle, and inner ear, with their corresponding functions, and I will show them everything. Sounds good? So we start with the outer ear. And the first structure in the outer ear is pinna, or follicle, which functions as a device to channel the sound into the ear. On the model, you can see follicle here. That's where the whole here. And if you look at the shape, you can see that it's kind of spiral shape, allows sound to be channeled into auditory tube. Okay. Now, this structure has at least 2 names that we need to auditory tube, or auditory canal, or external acoustic means. Many names are there. So here, look, this is an external acoustic means. It's covered with the skin or hair, and it has ceruminous glands that form sweat glands that produce earwax. Okay, so far, we're good. So, in terms of the function, I would say maybe containing dirt and microbes by producing earwax. Okay. Now, these 2 structures represent our. What I just realized, like seriously, just realized, is that we are talking about sound, but we never really defined what is sound. Okay? So I'm going to put quote unquote a definition of sound here in the corner. Sound is the mechanical wave. Okay? It's a mechanical wave. And as any other wave, it can be characterized by its amplitude and frequency wavelength. Okay? Now, look at this. This is the wavelength. Okay? Does that make sense? That's called loud. So frequency is called the letter mu equals 1 divided by. Well, no. I'm not going to ask this formula. The speed of sound divided by the wave. Okay? Does that make sense? Now, this is basically physics. Okay, so I'm going to specify some things. Wavelength, measure it in the units of length, right? Like meters. Speed of sounds, measure in meters per second. And frequency, measure it in hertz. And 1 hertz is 1 wave per second. Does that make sense to you? So, to give you an idea what different sounds are, I think I asked last time. Do you play musical instruments? Or used to play? First A, the first octave, the sound that orchestra uses to tune in, 441 hertz, 141 hertz. The lowest threshold for human ear is 20 hertz. The highest threshold is 20,000. We actually are really good in terms of ear, like really good. Human ear is amazing. Okay? So frequency and wavelength represent pitch. Okay, amplitude. Amplitude represents loudness. Am I clear so far? Okay. Moving on into the inner ear. Middle ear. And the first structure is tympanic membrane or eardrum. The whole function is vibration. Here. See, that is an eardrum. Now, when eardrum vibrates, it transmits its vibration to 3 auditory ossicles. Malleus, or hammer, which is attached to tympanic membrane. Malleus transmits vibrations to incus, or angle, and incus transmits vibrations to pes, or sternum. So you can find those auditory ossicles kind of here. I can't really use the model on the video, but I'll show you. I've got malleus attached to the membrane. You've got incus, okay, or handle. And we've got stapes or sternum. Okay, auditory ossicles vibrate and they transmit vibrations into the inner ear. So far, we're clear. We're going to talk about inner ear in a second, okay? Because we need to complete the beginning. This transition, tympanic membrane values into states, if that makes sense. Really important feature is that throughout this whole transition, the frequency of sound is not changed. So frequency of vibrations of tympanic membrane is the same as frequency of sound. Same is true for all auditory muscles. Okay. Now one more thing. This whole structure here is middle ear. Sometimes the space in which this is located, this space where my finger is, it is a tympanic cavity. Okay? And tympanic cavity, as you can see, has another tube. You see that tube here? This is called Eustachian or pharyngotympanic. Eustachian or pharyngotympanic tube connects middle ear and the pharynx. Opens on the side of the nasopharynx. Now, did you have, well, I guess everybody had ear infections. They're kids, right? Ear infections, the result of migration of mucus containing microorganisms from the pharynx into the ear. Does that make sense? In kids, this tube is more flat, so it's easier for microbes to reach there. So far, any questions? Good? I'm going to kill it. Anyone's interested? So now it's time to talk about inner ear. Also known as labyrinth. Okay? Now, I'm going to be honest with you, explaining how the inner ear is generally devised is challenging. Okay? Because it requires a lot of imagination. Okay? So we're going to, until you get it, just tell me, no, I don't get it. Can you explain it again? Deal? Okay? So there are two labyrinths. One, I think I have an idea how to explain. Let's do general structure. How about that? There are two labyrinths that comprise inner ear. One is so-called bony labyrinth. So this colored part is a bone. Okay, so look at this. You see bone here? Okay? Do you see these depressions? So this is what is called a Boney labyrinth. Let me ask you, it's a technical Boney labyrinth is just empty space. I can see the confusion. No. It's a legitimate confusion. When I want to elaborate. When we say skull, okay, skull has a particular shape, right? It's a bow. It's a bow. It's a skull. Okay. Now, I think it's going to take a lot of analogies to clear the confusion. Do you know what orbit is? Or ISO? Okay, ISO, right? It's the place where I is. Make sense? But in fact, it's just empty space of a particular shape. Does that make sense to you? Like, it is formed by several bones, like maxillary bones, zygomatic bone, frontal bone, lacrimal bone, whatever. But in essence, you can't make a model of eye solid. Well, you technically can. What you need to do, you need to take somebody's eye, right? Take some plastic, pour it into the socket, let it solidify, take it out. There you go. Like a cast. Does that make sense? So what you see here is a cast. Imagine that someone poured a plastic into an empty space. Does that make sense? And that's what we've got. You understand? So technically speaking, Boney labyrinth is an empty space. Now, Boney labyrinth is filled with the fluid called areolin. Nothing special. It's like extracellular fluid. Okay. Now we come to really important. Inside of the Boney labyrinth is membranous labyrinth, and it is a legitimate structure. It's a tube. Okay. So this is membranous labyrinth. I think I misspelled labyrinth. I think I missed Y and R. But it doesn't. Okay. I have no clue. Whatever. You understand what I'm talking about. Labyrinth, like in the movie, like a maze. Okay? And inside of membranous labyrinth, there's a fluid called endo. Good? Now, what I want you to understand very clearly, endolymph is like intracellular fluid, in particular, has very high concentration. Okay. That will come really important. Okay. So when we look at the structure of this is inner ear. Remember how I was talking about the fact that when you have a model of Boney labyrinth, it's basically a cast. You see this white stuff here? That's the cast. That is empty space. Cool? You see the blue things. Those are elements of membranous labyrinth. All right? So we can match the parts of the bony labyrinth and membranous labyrinth together, basically saying what they are to each other. So bony labyrinth has three parts. It's cochlea, vestibule, and semicircular canals. Cochlea, vestibule here in the center, and semicircular canal. Now, inside of the cochlea is so-called cochlear cell membranes. So-called cochlear duct, or scala media. Inside of the vestibule, two structures, saccule and utricle, and inside of semicircular canals, semicircular ducts. Question?
So, for the bony labyrinth, is it this structure or is it like the shape of it? Anything that has?
Strictly speaking, shape. But if you would look at this one, this part goes beyond the actual empty space. Does that make sense? So this part, specifically looks like we feel a little bit of bony labyrinth with plastic. Does that make sense to you? But when you look at the shape, it gives you sort of better overall understanding of how it looks anatomically. Let me kind of do another approach. If you somehow can scrape out all membranous labyrinth, what you have left, that space, that cavity, is going to be bony. Clear? Not pay so much attention to this. So, cochlea is responsible for hearing. Vestibule and semicircular canals responsible for balance. And we put stuff and then little okay. And these two now look, what's inside cochlea? Cochlear duct. What's inside cochlear duct? A hearing organ. What's inside vestibule? Saccule and utricle. What's inside saccule and utricle? Special sensory organ called macula, which senses linear acceleration. What's inside semicircular canal? Semicircular ducts. What's inside the ducts? Special organs called cristae polaris that sense rotational acceleration. We're going to talk about this, don't worry. Okay, I just want to show you this kind of Russian doll type of structure. You clear? Good? Now let's talk about hearing. The function that is carried out by cochlea. This shape, does it remind you of something? Sure, seashell. How would you call this shape? It's a spiral. Very good. It's a spiral. So now imagine like a like a coil, right? Sort of a coil. Are you following me? Now let me ask you this. If something is spiral, can you hypothetically straighten it up? Yeah. Yeah. Imagine that you take this spiral and you straightening it up. Okay? And we don't do it like it doesn't happen in real life, but we just do it for the simplicity. So it turns out now this part here shows you the boundaries of the bone labyrinth. That makes sense. But inside the bone labyrinth, there will be membranes, right? So this membranous labyrinth inside of the cochlea is cochlear duct. Now, this model here presents a cross section of cochlea. So imagine somebody took a knife, got it like this, and looked at this section. Be clear. So, and if you would do that, you would have sort of three compartments. This compartment, you will see this compartment, right? This compartment and this compartment. So this top one is right here, and it's called vestibular duct or scala vestibula. Okay? Vestibulochronology. This structure right here is a tympanic canal or scala tympani. And this structure right here, the whole thing, is cochlear duct or scala media because it's in the middle. So vestibular, that is tympani. So far, you with me? Awesome. Now, what's here? Here is oval media. Sound enters here. Now, if you would take this tiny little things, models here, and you will look at the stirrup, the bottom of the stirrup, exactly overlays over the window. So when stirrup vibrates, that makes sense? Stirrup vibrates. It sends waves into the skull vestibule. Now, skull vestibule, what does it feel like? It's filled with fluid, right? Can fluid conduct waves? Yeah, and it will. Does that make sense? So those waves will keep going to the skull vestibule. And then something interesting. So if, hey Jake, I'm going to change it to slightly different. Okay. So something interesting happened. If if you do not if the sound is in the hearing range, are you following me? In the hearing range. It's not a perfect analogy, but work for us. It will take a shortcut through the skull and get into the skeleton, and it will lead through the rounding. Few questions before we move on. So state that bone, the stirrup bone, in which part of the ear is it located? Inner ear, outer ear, or middle? Huh? Middle, absolutely, it's in the middle ear. So sound gets in the oval window from the middle ear. Where do you think sound gets out of the round window? Back in the middle ear. Does that make sense? So we can say from the middle ear into so far. Does that make sense? Good. Now, what if we can't hear the sound? What we usually say is that sound is not close. Oh, media. So we're going to can't hear. Not. Sound just goes from skull to vestibular to skull to spine and then gets out. Right clear? Now that sounds a little arbitrary. How the hell do we know? Can we hear it? Can we not? When does it cause? When it does? Now it's good that all of you played musical instruments, because my next explanation will make a lot of sense to you. Are you familiar with the, like, especially when people play electric guitar, sometimes they intentionally do the feedback. Ever seen that? No? They have a massive loudspeaker where the guitar sounds are coming from. And they can come to that loudspeaker very close. And then the sound waves from the loudspeaker will start vibrating guitar strings, producing extra sound, and it will be like positive feedback. Does that make sense? Like, sometimes it's intentional, sometimes it is not. You following me? Now, when we say that sound closes, it doesn't close. Here's what happens. Our cochlear duct here, the green part, this membrane specifically is called basilar membrane. Basilar membrane consists of multiple string-like structures of different length. Does that make sense? Longer fibers will respond by vibration to lower sounds, sounds with a longer wavelength. Does that make sense? And shorter fibers will respond by vibration to the sounds with the shorter wavelength, higher pitch. Am I clear? Have you seen this little, what's that percussion instrument with like little blades? Huh? Xylophone. Thank you very much. You've seen xylophone, right? Each plate produces its own unique sound, the shorter the plate, the higher the pitch. Got it? So your basilar membrane is organized like a xylophone. You have a lot of fibers of different length, and each fiber will vibrate to a particular pitch. We good? Good? Okay. So when we say we can't hear the sound, it's not because it just doesn't take a turn. It means that we don't have a fiber that is long enough or short enough to respond to that frequency. Does that make sense? Like in some people, certain sound range may be blunted. Sure thing. Okay? Why it is blunted? I don't know. Maybe the fibers got destroyed or something. Are we clear? I need to put a little note for. I forgot to tell you something, and I just so don't write anything. Just note for myself. So far, we good? Now, what happens then? What happens? On the basilar membrane, we have so-called hearing organ, or organ of Corey. And this membrane is called vestibule. Okay? So far. Good? Okay. So let's expand on what hearing organ is composed of. I'm not going to talk a lot about anatomy. I'm going to talk about hearing organ, and then we'll take a break. Okay? So this model here, this is hearing organ. Okay? So this is vestibular membrane. This is basilar membrane. And you can see that hearing organ is located at the basilar membrane, like I drew here. Make sense? Now, basic conceptual understanding here is this. So you've got basilar membrane. On basilar membrane, you have so-called hair cells. Each on the surface of each hair cell, there are cilia. Okay? So the shorter ones are called stereocilia. The longer ones are called kinocilia. Kino means movement, kinetic. Make sense so far? Now, the top of kinocilia are embedded in so-called pictorial membrane. Pictorial membrane is pretty sturdy. It's short. You can see it on the model. Okay, it's short. Can you see how well it is affixed here? Sorry, pictorial membrane. That's vestibular. Pictorial membrane, you see? It's short and it's pretty sturdy, so it doesn't really move a lot. Okay, make sense? So in response to vibrations, only basilar membrane will move. Now I'm going to represent what's going on using my hand. So imagine that my forearm is a basilar membrane. Okay? My palm is a hair cell. And my fingers are stereocilia and the kinocilia. I can make my index finger to be longer to get it, right? Kinocilium is embedded into pictorial membrane. Okay, dictorial membrane holds it pretty hard. That makes sense? Sound comes in, vibrations. And what happens to the basilar membrane? It starts to vibrate. Does that make sense? Now, I'm going to vibrate like this. Okay? What happens to my fingers? They bend. Forget about them being together, but what they do. What did I do with them? I bend them, right? They bend. So stereocilia start to bend. Look what they have. No sound. They like this. Sound. And they like this. Does that make sense? Now I'm going to write down the steps that lead to the generation of graded potential. So I'm going to skip all these steps, all the windows, call it vestibuli, and I'm going to get to the vibration of basilar membrane. Are you good with that? Basilar membrane vibrates, which leads to bending of stereocilia. Okay. Bending of stereocilia opening of mechanically gated potassium channels. Okay? Now, what fills up membranous leverage? Pendulum. Cochlear duct is a part of the membranous leverage, right? So your hearing organ right here is surrounded by pendulum. Am I clear? And which ion is a particularly high concentration? Potassium. So since potassium concentration in pendulum is particularly high, potassium starts to diffuse into the hair cells. Are we clear? When positively charged ion diffuses into hair cells, how does it change the membrane potential? Makes it more positive ion. Positive ion diffuses into the cell, membrane potential becomes more positive, which means depolarization. Now, depolarization opens voltage-gated calcium channels. Since concentration of calcium outside of the cell is higher, calcium diffuses in neurotransmitter in response to calcium. Does it make sense? Now, I'm going to tell you right away. So we already figured out how you can hear different pitch. Remember different fibers on the basilar membrane? Remember that? Different length. So, for instance, voice like this the lower waves, will lead to vibration of longer fibers. In the voice like this, the higher voice will lead to the vibration of shorter fibers. So this different fibers will be included. Does it make sense to you? What about amplitude? Well, look here. Higher amplitude responds with more intense vibrations. Does that make sense? Which means there will be sort of bigger waves going through scala vestibulum. This more intense vibrations will lead to more intense vibrations of basilar membrane, which means stereocilia will stay bent longer, which means more potassium will get into the cell, which means depolarization will last longer, which means voltage-gated channels will be open longer, which means more calcium will diffuse, more neurotransmitter will be released, and the signal generated in the neuron will be more frequent. Frequency of action potentials will increase. Does that make sense? This is how you hear a louder sound. You good? Before I forget, I have note for muscles. In addition to inner hair cells, you also have so-called outer hair cells. Outer hair cells are not sensory. They, in some way, motor. So they are arranged in the same way. The hairs are embedded into the pictorial membrane here. See that? But what they do, when sound becomes very loud, these cells, they stiffen. And they don't let basilar membrane vibrate too much. Does that make sense? Because if vibration goes out of control, it can damage your hearing structures. Basically, if the sound is too loud, it can physically damage your hearing organ. Outer hair cell, by stiffening up, limits the vibrations of basilar membrane. Does that make sense? Preventing damage to hearing organ. The trade-off, the sensitivity to sounds decreases. Have you been to a real loud concert? Okay. I went to Nepal Deaf concert, and I was like that close to the stage. I don't know why. Next day, I had the lecture, and I was yelling, and I asked students, please yell at me, because I cannot hear anything. It lasted for a couple of days. So it's essentially a response from the ear to limit the vibrations of basilar membrane to avoid damage. But then this response does not go away immediately. It takes a while. Does that make sense? Questions? I'm going to take a break. We'll come back. We'll talk about deafness, balance, and muscles. I know what I want to say. Okay. First, just talking about, before we move any further, questions on this one. That is, I mean, I don't say kind of important, that is really important. That you can do it in the sequence. Want to take a picture? Sure. Let me pull the recording. So this is the great example of, when you can do a brain dump. That would be okay. Next time, next week when you're going to have a test, just brain dump. It'll be fine. Okay. Second thing, first, you understand how we determine the pitch? Different fibers in a basilar membrane vibrate at different frequencies. What allows us to determine amplitude? Intensity of vibration. Now, a couple sort of minor things. First, if you would look at the size of, look, that's the size of tympanic membrane, right? That's the size of tympanic membrane. This, under the stirrup, is the size of the oval window. Okay? You see that oval window is much smaller than tympanic membrane. That actually amplifies the sound. That allows us to pick up really quiet sound. Does that make sense? Second thing. Muscles. This is not random, it's just not really in here. I simply thought about it. So remember 3 auditory ossicles? Malleus, incus, and stapes. It turns out there are 2 muscles. One is called ventral tympani, and another is called stapes. That serve the same purpose as the outer hair cells. When sound is too loud, they limit the vibration of the auditory ossicles. So they stiffen up and don't let auditory ossicles do with the higher. Got it? How do we determine the localization of the sound? So for instance, if I am here, I'm here, and look, Katie, her left ear is closer to the source of sound. Does that make sense? So sound will reach the left ear a little bit earlier, and it will be a little bit louder. And your brain can pick up those tiny little differences and localize the sound. Does that make sense? This is sound localization. Deafness. Some of that stuff. Actually, I'm going to leave it the same. Right? Deafness. You have conduction deafness. And you have sensorineural deafness. So when someone has sensorineural deafness, the structures that can be affected are hair cells or cochlear nerve. So cochlear nerve is the part of the vestibulochronology nerve. It's the cranial nerve. I think it's 8. Yeah, cranial nerve 10 is vagus. Yeah, cranial nerve 8. I'm not agnostic. Cranial nerve. So damage. Can be tumor, can be inflammation. From the really loud sound, hair cells can be damaged. That make sense? For conduction deafness, the structures that can be affected are tympanic membrane and auditory nerves. So basically, or remember, you put something in your external acoustic meters and they can't hear it. So basically, when you put the soundproof earphones, whatever. you call it. Yeah, earmuffs. Yeah, that's you emulate conduction. That make sense? Hearing aids exist for both. There are some hearing aids that kind of redirect the sound to the skull bones. Hearing aids that generate electrical impulses and basically transmit it directly to the mind. Good? Clear with a definite. Talk about balance. So we're going to start with cochlea. Which contains, remember, cochlea, I'm sorry, not cochlea, vestibule. Which can, and remember, vestibule is the part of the bone level, right? So vestibule contains two substructures, which are saccule and utricle. So saccule senses vertical linear acceleration, while utricle senses horizontal linear acceleration. Okay, now I'm going to draw here schematics of the sensory organ that is common for both, and that one is called micro. Okay, so you have basilar membrane. Okay, so it's membrane. And you have hair cells, all the same story. Okay, do you see hair cells? But this time, hair cells are embedded into a slightly different membrane, which is called otolith membrane. Otolith membrane is very heavy. Okay, it is heavy because it contains a whole bunch of crystals of calcium carbonate. Does that make sense? Now, let's figure out what happens to otolith membrane when this whole construction is moving to the left. So I'm going to imitate this image, okay? So my head, and you definitely know what I'm talking about. My head is otolith membrane, right? The rest of my body, see how comfortable I'm sitting? The rest of my body is hair cells. And membrane, whatever. So everything below otolith membrane is everything below my head and neck. Okay? Now I'm telling you, I am the passenger in Ford Mustang. Okay? And the driver next to me puts it in the drive position and floors the gas. Can you imagine that? What's going to happen to my head? Yeah, this is what's going to happen to me, right? Because the seat will kind of hold my body, but if my head, well, in Ford Mustang, I will hit the headrest. But if I'm sitting on something like that, I don't have a headrest, so my head will go back. We clear? So when this thing moves to the left, otolith membrane does not, due to inertia, due to the fact that it's heavy. Make sense to you? So it kind of flinches backwards. You know what happens to those hairs? They bend. And remember that pathway that we drew? They bend. The potassium channel's open. Remember, it is inside of the membranous labyrinth. So that's endo. Potassium channels open. Potassium diffuses into the hair cells. That leads to depolarization. Depolarization opens calcium channels. Calcium flows into the hair cells. Leads to the release of the neurotransmitter. Make sense? Got it? Now, a bit of a digression. It takes me a while to make you answer the question. And I think the main issue here that you don't deliver this. No, seriously, you're afraid to say something that is not correct. It's fine. So say, okay, it's okay. This is the environment where nobody's going to laugh at you saying something incorrect. It's not a high school. People are not going to think that you're stupid. Yeah, I've been to high school too. All right, so here's the question. Look at this description on top. Look at this picture and tell me, this picture illustrates a macula found in saccule or found in utricle. Good try. Why? It is utricle. Why? Because it's moving horizontally. Bingo. To make the same illustration about saccule, what do I need to do? I need to make it vertical. I need to turn this picture 90 degrees. Does that make sense? Good. Next question. Have you ever well, I'm embarrassed since I don't know the third form of past tense for fly. Have you ever been in a plane? Okay. And imagine you are at 30,000 feet, no turbulence, no nothing. And hypothetically, you don't hear the sound of engines. Can you tell that you're flying, that you're moving? If the plane, yeah. So if plane moves, no acceleration, make sense? No acceleration, no turbulence, you hear no sound, you can't really tell that you're moving. Make sense? So when there is no acceleration, otolith membrane not moving. The deal is, it's always like when I do this, it's always tiny little accelerations, and they're picked up by the otolith membrane. Are we clear? Got it? What's even more interesting, if you move forward or backward, up or down, you can imagine that otolith will move in different directions, right? Turns out that if it moves one direction, potassium channels more of them will open, and so it will depolarize and release more neurotransmitters. We move in another direction, some potassium channels will get closed, less potassium will move in, less neurotransmitter will be released, because cell is hyperpolarized. So frequency of action potentials will be higher in one direction and lower in another. And this is how we can tell we go up, we go down, we go forward, we go backwards. Am I clear? Now, what about circular accelerations? Where's semicircular canals? So semicircular canals, they sense basically movement, any movement that is like rotational movement in any plane. And I want to ask you a question, which is kind of 5 out of 10 question. It's not an easy question. Maybe even more. We have 3 semicircular canals arranged in that particular way. Why? Any idea? It's not up, down, forward, backwards, and left, right, because it's circular. No. You got the essence. The only thing that I would correct you with is the direction of a movement. But you were absolutely right. 3 planes. This plane, so basically sagittal plane, transverse plane, and coronal plane. Does that make sense? Because then combination of signals from 3 semicircular canals allows us to determine the direction of movement in 3D space. Clear? So, how does that look? Again, a membrane. Hair cells. Sorry. These hair cells are embedded into a gel-like structure that is called ampular nucleus. Looks like a mushroom. And this whole thing is called crista ampullaris. You good? Now, again, crista ampullaris is inside of the membranous labyrinth. Make sense? Look at the semicircular canal. When you start moving one way, the fluid temporarily, due to the inertia, moves the other way. Make sense? I don't have the transparent beaker, the empty transparent beaker, but you can imagine we will take a beaker and fill it halfway with water and then slide it. The water will go in the opposite way initially. Does that make sense? That's what happens. It flinches ampullary cupola. It bends hair cells, and the whole story repeats itself again. Make sense? It's channels open, or some of them closed. So cell, depending on the direction of motion, is either depolarized or hyperpolarized. Okay. Frequency of action potential is either increasing or decreasing. You clear? Make sense? Now, last bit, we're going to finish. Last bit, disorders. So there are 2 really. Oh, okay. Let's do disorders. Then one really important one. Disorders: motion sickness and Meniere's disease. So in Meniere's disease, you have a lot of fluid, too much fluid, accumulating in your membranous labyrinth here. Membranous labyrinth swells, and treatments usually include somehow reducing the amount of fluid in the membranous labyrinth. but many people ultimately have to have it removed, which basically, removal of the entire thing, including cognitive, so people become deaf. They balance it themselves. Does that make sense? Now, can you excuse me for 1 second? I think I know what it is. Okay, now that's Meniere. Motion sickness. The cool thing about it is that we don't really know what is. We don't really know the exact mechanism. I think it's kind of a learning moment here. We often tend to think that, oh, modern science, yeah, we know shit like that. Motion sickness was around all the time, right? We don't know how it works. What we do know is that most likely it's the mismatch between your visual input, what you see, and vestibular input, what you feel. Are you following me? You all drive, right? And I don't know what your response is going to be, but I'm expecting certain response. If you drive, do you get motion sickness? Like while you at the driver's? No. And I tend to drive a lot. If you are in the passenger seat or in the back seat, especially if you're like looking at your phone or reading a book or something, did you ever get some motion sickness? Because especially in the traffic, in the heavy traffic in the city, there is stop and go. When you sit and read the book, what does the book tell you? The book tells you, dude, we're not moving anywhere, right? Like you don't see, like the book is right there. Your eyes are telling you, we here, not going anywhere. But your vestibular apparatus, vestibule and semicircular canal, they tell you, oh yeah, we are moving all right. Okay? Does that make sense? So this is why you get motion sickness. Why you get motion sickness often, like on a ship, especially when you're inside. You're inside, everything's like you're moving, but your visual stimuli don't really suggest that you move. Okay? And how you treat it, it was perfect. I had basically a clinical example. I was on the small motorboat, and I was in the boat doing some stuff. It was pretty rocky. I had motion sickness. I peek out, I look at the lake, there's a Lake Erie. I get better. The moment I get inside, I get more. Okay? Because mismatch. Now, how exactly through which structures and whatnot, we don't know. It stimulates vomiting center in the building kind of stuff. That makes sense? Last little bit that I wanted to mention. So vestibular apparatus, obviously, tells you whether you are moving and what kind of position you in, right? You understand what I'm saying? Often we say that vestibular apparatus is essential for balance. For instance, it is known that when people are drunk, the composition of endolymph is likely changing. So it messes up with the potassium diffusion, and it messes up with the signaling through the hair cells. Does that make sense? Now, when people are drunk, they kind of lose the balance. Are you following me? So, does that mean that vestibular apparatus controls your balance? No. What it does, it sends the signals to cerebellum and to the basal nuclei and to the motor cortex, telling them where you are at now. Am I clear? When people are drunk, the signals from vestibular apparatus become incoherent with an actual situation. Does that make sense? Like your apparatus sends signals that you're falling, but you're not, and so on and so forth. And that is why people lose impact. It does not control, it doesn't control the muscles. Right there. That'll be it. I can start those. And I'm pretty positive that I can deliver all the bone and muscle material before Thanksgiving. And I am really hoping that we can do lecture exams before Thanksgiving. So then the thing that will be left are anatomy things. My plan is that you're going to have anatomy exams after Thanksgiving, maybe just like a massive final. Bone and muscle anatomy exam like together. 2 separate exams, but on the same day. And what I'm going to do, since it's in the afternoon, I'm going to drive to campus. And I'm going to broadcast from here, showing you the bones, reviewing the pictures. Does that make sense? So you're not getting confused with the pictures on the deal.